Well, welcome everyone. So today we're going to talk about OpenCL, a framework for heterogeneous computing. And I'll just start with an acknowledgement of country. So Pelagos would like to acknowledge the Whadjuk people of the Noongar Nation, the traditional custodians of the land from which this presentation is being broadcast. We pay our respects to the elders past, present, and emerging. We also extend this respect to you, the audience, for your positive contributions in making this world a better place. So I'll just do my first vendor slide. That's the only vendor slide that I've got, but I'll just explain a bit about my background, what I'm about, and how I'm helping folks here in Perth. So yes, I do have a HPC background, and that started in 2006, where I was doing some CFD simulations of black hole jets. So that was using a Fortran code, and it's a Fortran code that is also used for other purposes involving thermonuclear flashes. So yeah, so that was interesting work, and that was my first introduction to HPC and using MPI on lots of processors and things like that. Moving forward to 2013, that's when I finished my doctorate, also doing CFD simulations of an expanding supernova remnant. So this is an infographic from that work, and you can see there's an outer shock wave and there's an inner shock wave running into this torus of material surrounding, that surrounded the star prior to the supernova explosion. Moving into postdoc, I worked on boundary conditions for my research group. So here's a seismic wave sort of being absorbed at the edges of a simulation. And boundary conditions are a way to save compute time, particularly within the seismic resources sector. So yeah, worked on boundary conditions, and to do this, I was working with technologies like C++, CUDA, Python, but also doing some HPC cluster procurement and administration. So in my business now, I'm really about helping folks with their scientific computing needs. Now this can be for academia, but it's also for industry as well. So I can scale across both sorts of modes of work. So I do some Python training, and I've got a full suite of courses developed right through from beginner courses through to using GPUs with Python. I'm also a software developer and consultant in scientific computing, and I like to work with highly parallel systems. I was an OpenCL mentor for the Pawsey hackathon in 2018. I've worked with universities doing software development and HPC support, government, been doing some training with them, oil and gas, helping to get the best out of the infrastructure that they have. And currently, I'm working for some mining services doing software development with Python and GPUs. So there's my email address down the bottom and the website that you can go to if you want to check out Pelagos a bit further. So today's talk, I'm just going to give an introduction to OpenCL. Now, I wasn't sure the level at which people are entering today's session, so there might have been some scientists or maybe some non-application experts within the audience. So I'm going to pitch it at a fairly basic level to start with. Then I'm going to talk about the implementation roadmap for OpenCL, how our vendor implementation's going, what's the health of OpenCL. We're going to talk a little bit about OpenCL and CUDA, some pros and cons. And then we're going to launch into a demo, if we've got time, doing 2D image correlations with OpenCL in a way that goes across the different hardware devices that I have on my machine. And we're just going to finish with OpenCL at Pawsey and our proposed training course that we're going to do mid next year. So what is OpenCL? Well, I guess we've got to think about hardware to start with. So every compute device, so that's a GPU, a CPU, an FPGA, is made up of a number of compute units, or otherwise known as cores. Now, within OpenCL terminology, each compute unit provides a number of processing elements or hardware threads that can run software. Okay, so maybe in a CPU, one core might present 2 hardware threads to the operating system. So a hardware thread is a word for processing element. Okay, so that's what we're going to use within OpenCL terminology. So to give you an idea of what's going on perhaps in a GPU, I've just lifted this image off Wikipedia, and it's a NVIDIA GP102 die that would be part of the Pascal architecture, the Titan XP GPU, for example. And that has 30 compute, 30 compute units, and these are otherwise known as streaming multiprocessors within CUDA terminology. So each of those compute units presents 128 processing elements to the operating system. So there's a total of 3,840 processing elements available for use doing parallel compute work. So what is OpenCL? And I think we can first start with the idea of a kernel. So the kernel is some compiled C or C++ code that runs on a processing element. So that's that hardware thread, and it performs a specific task. So on the right here, we have a kernel, and this particular kernel is going to be doing an image correlation. So we've got our source image, our destination image, and we've got our kernel, and this is just some C code here that digs out the right offsets or positions into the image and then performs that loop over the kernel. And what it does is it does a sum, so a multiply and add, a series of multiply and adds, and it puts the result back into the destination image. So that's what a kernel is. So a kernel is a very specialized piece of code that runs on a processing element. So OpenCL itself is just a specification. It's just a document. But an OpenCL implementation is a way to run a kernel instance at every point of a user-defined virtual 3D space called a grid. Okay, so this is a grid here, and we have predetermined what the size of that grid is. So that defines your sort of virtual computing space or iteration space, as you would say. Now, within OpenCL terminology, grids are divided into work groups. So these are these blue borders here, these define work groups. And within each work group is what they call a work item. So every work item is synonymous with a kernel invocation. So a kernel is being run for every work item. And what OpenCL does, and indeed what CUDA does as well, is that they map kernel instances to available processing elements as they become available. Okay, so I've, with this grid here, I've said that this work group here has already been completed, but I've purposefully left some of these elements here orange. So this work item is being completed, this work item has been completed. Now, on some devices, the work elements work in teams, but that's not always true. So you can have barriers to make sure that all the work items end up at the same place in the code. But I'm just stressing here that a series of kernels will only complete once this whole grid has been visited. by kernels. So yeah, so that's what an OpenCL implementation does. It maps visitations of this kernel to every space in your user-defined grid. So using that position of a work item within a grid, you can work out where you are within a device's memory allocation. And so that's how you can access memory inside a compute device. So you're using your position within this virtual space to access memory at a certain location within your compute device. So this is how executing kernels can read and write memory. So OpenCL is currently mature, and it's supported on a wide range of architectures. So ranging from your laptop, your mobile phone, right through to exascale devices. So this is the NVIDIA A100 GPU, and that's currently scheduled to go on the supercomputers Perlmutter and Jewels. The Intel GPU offering is the Ponte Vecchio, and that's currently going to Aurora and Supermuk. And the AMD Instinct GPU, the MI250, that's currently going to Setonix next year, but it's also going to Frontier and Lumi. And the common denominator that works on all these devices currently and works well on all these devices currently is, of course, OpenCL. So that's something to consider when you're thinking about your code investments for your research group, for example. What devices can it run on? And so, yeah, I'm making the point that OpenCL currently works on all the devices being slated for exascale architectures right now. So a typical accelerated application goes according to this formula. And this is true for SYCL, this is true for CUDA, this is true for OpenCL. So at the start of your run, a compute device is discovered on your system. Then kernels are JIT compiled for those available devices. So that compute kernel that I talked about right at the beginning, that would be compiled for every device that is available on my system, or at least according to the ones that I want. And I'm just going to go to a question. Wasim says, in terms of OpenCL implementations, are these typically developed by the device vendor or a third party? Do you mean the kernels, Wasim? Or do you mean, yeah, what are you referring to there? Oh, right. So yes, the compiler, I think it does depend on the vendor. I know that NVIDIA produces its own OpenCL compiler, which compiles to an intermediate representation called PTX. And then that gets compiled down to machine code. Now, I think with the LLVM compilers that are a part of the Intel implementation, they compile down to SPIR-V, as far as I'm aware, and then from SPIR-V you can go back down to the hardware representation. So yes, the answer is it can be open source and it can be vendor specific. Yeah. Yep. So memory is allocated. So the next step 3, is memory is allocated on the compute device, and data is then copied from the host to the compute device. Kernels are run. Kernels are waited on to finish, and then memory is copied back from the compute device, and then information can be exchanged, such as to hard disk or via MPI or whatever. Then steps 3 to 8 are repeated as many times as necessary. And then when you're done, you just clean up resources and exit. So that's kind of like the template for your average your average accelerated application. Okay, so just talking about some concepts now within OpenCL. So within OpenCL, you start off with your platform, and that provides interfaces through your drivers to the devices that you have on your system. Surrounding that is a context. Now, a context, as far as I'm aware, provides information on stores information on what's going on with your devices. So the status of buffers, the status of kernels, etc. Now, within OpenCL, there isn't so much a concept of a buffer that lives on a device. A buffer is kind of defined within a context. And then during the execution of the OpenCL application, this buffer is then migrated to the particular device in question. So I guess that's a little bit different to CUDA. So we have CUDA, we have our context, and then we have buffers that have, a very specific location on the particular devices there. So moving over to programs. So programs contain kernels, and there's a program for every context. So there has to be a program for every context. That is, I think it's every context and device, but yeah, that is on the system. And so that's where your kernels live. So you bring in your source, and then during execution of your OpenCL application, you compile these, and they become associated with contexts and devices. Moving up one level, then we have these sort of like levers on your available hardware. These are the command queues. And so when you want to upload and download memory to and from your devices, you use these command queues, and that's how you specify which device that they go to. Okay, so you've got these buffers that live inside the context, but when you enqueue a copy operation to a particular command queue, that command queue is associated with a specific device. So that's how it chooses where the memory goes. So these command queues accept copy operations. They also accept kernels as well. So this is how you get a handle on, this is how you can schedule work to your devices. A similar thing occurs within CUDA, and these are called CUDA streams. And yeah, they do pretty much the same thing. Now, just above these are events, and these events, oh, sorry about the noise going on outside, it can't be helped. But events, yeah, events, they are triggered when a particular command that has been sent to a command queue exits. Okay, so this is how you can wait. This is how you can wait on work to be completed within a command queue. Similarly, in CUDA, you also have events as well. So that's the general high-level concepts of what is going on in an OpenCL application. And I just want to talk now about the specification. So the initial specification came out in 2008, and that provided all the functionality that I've just described to you before. Specifications evolve, and yeah, so this is what happened with OpenCL. So with version 1.1, we got rectangular copies, so that you could copy rectangular regions of your buffers, so like 2D and maybe even 3D rectangular regions of your buffers. So that was quite useful. It also provided user events and 3-component vectors, but it also introduced thread safety, which is really, really, really important. So that meant that the only thing that wasn't thread safe was adding arguments to a kernel ready for invocation. So yeah, so thread safety was really important. Specification 1.2 introduced device partitioning. Now, I think really device partitioning is really cool because it can allow you to create sub-devices, for example, that share an L3 cache, for example. So in your AMD chip, you have these core complexes and they share L2 and L3 caches, for example. So within your device, you can create sub-devices that share caches, for example. So this is how you can group, this is how you can group compute on your particular device. So yeah, 1.2 also brought in offline compilation, so you could make binary kernels. That's kind of good if you want to hide some source. It also brought in IEEE 754 compliance. So that means that you're getting the same results across all your devices. So that's really important for scientific work. Also some debugging functionality, printf in kernels. So 1.2 is kind of like the de facto standard for OpenCL. It's kind of been that way since 2011. In 2013, a major breaking change was introduced. That's version 2.0 of the standard. And this introduced shared virtual memory. So I think a similar thing is already being done on with CUDA, namely unified memory. Okay, so shared virtual memory just allowed you to work with pointers, like one pointer on your host and then the same pointer on your compute device, and you were able to access the same memory, whether it lived on your compute device or whether it lived on your host. So that's what shared virtual memory was all about. Being able to run kernels from kernels, so version 2.0 was also brought that in. Version 2.1 brought in SPIR-V. So SPIR-V became mandatory as part of the specification at that point. Now, SPIR-V is an intermediate language. So your compiler would compile then to SPIR-V, and then another compiler, as far as I'm aware, would take over and then compile down to machine code. Okay, so SPIR-V became part of the standard. So it became mandatory. The same with shared virtual memory. Okay, so these two things, in my opinion, became a problem for certain vendors because it was a lot of work to do, and there's a trade-off between what the customers want and what the specification requires. So yeah, so these two things was a lot of work to do. So there was a bit of reticence within industry to adopt versions 2 and onwards of OpenCL. So with version 2.2, there's nothing too much different, but they really went to town with complexity with regards to C++ functionality within kernels. Okay, and so supporting all that complexity, I feel was, got quite difficult for vendors to do all that. So at this point, OpenCL kind of stalled. There were some companies like Intel, for example, that were very, very focused on having the latest standard, but other companies sort of weren't so interested. I guess that's kind of like the drawback of designing by committee. So yeah, that's my only comment on that. So it was stalling until last year. So they brought out OpenCL 3.0. And what they said is that we'll make 1.2 canon, so that's pretty much as it has been. But everything else, such as SPIR-V and shared virtual memory, is an optional extension that you can provide if your customers would like to see that happen. So yeah, so lots of folks started to get on board with this again. So it has breathed new life back into OpenCL. And this sort of paves the way for the future of OpenCL. So things being optional extensions, and then once there's enough support for these optional extensions, then they'll become part of the standard. There was also a new C++ introduced for OpenCL, but I think the complexity of that is now handled by the LLVM. Yeah, so I think the folks at yeah, I think there's general, quite a lot of general support for getting SPIR-V implemented, because if the vendor implements SPIR-V, then that complexity of worrying about the C++ kernels and that sort of thing, that's handled upstream by your LLVM compiler. So if you can implement SPIR-V, then that's your job done as a vendor. So yeah, so I'm certainly keen for SPIR-V to be implemented by all the OpenCL vendors. So here's a not exhaustive list of vendor implementations, and this is sort of like how far each vendor got with their implementations. So I've said yes or no whether a particular vendor got to version 2.0, for example, with their OpenCL implementation. And I've put a sum here for some features that were implemented, so not all features were. So as far as I understand, there is good support now for version 3 from ARM, Intel, and NVIDIA. And I really look forward to AMD bringing version 3 support very soon. So yeah, so there was a bit of a drought. You can see this drought here of versions. So versions 2.0 to 2.2, there's a lot of no's here. But hopefully now that we've had this new version, this new way of doing things, that we will see more people getting on board with version 3. Oops. So a few comments about OpenCL versus CUDA. Now, I don't want to start a flame war on this because people have quite strong opinions, but these are just my own personal views. So OpenCL and CUDA, this is about proprietary versus community-driven standards. CUDA has historically been faster than OpenCL on NVIDIA hardware, and some people have done some research in this, and it has historically likely been due to differences in the way that the NVIDIA CUDA and OpenCL compilers produce that intermediate code PTX for the GPU. More recent results, and this is just going on my own experience, show that the gap is now around about 10%. So, so maturity has come a long way within the OpenCL implementation for NVIDIA. So that's really good. So CUDA/HIP is stable on 2 brands of compute device, and data parallel C++ support for CUDA/HIP is experimental. So what I'm saying is that, yes, SYCL's on the way, but it's not stable yet across all 3 platforms. Okay. So another comment, and this is what OpenCL has always had, is that OpenCL is portable to both CPUs and GPUs and across different vendors. And hopefully I'm going to demonstrate that very soon. So it can work on your laptop with your Intel hardware. It can work on your office machine with the latest and greatest NVIDIA, AMD, or Intel card. So remember that Intel's bringing out their discrete graphics cards very soon. It can work on whatever architecture is popular with your cloud providers, and it can also work on Pawsey's new GPUs. Some things that I found really cool about OpenCL was that it supported up to 16 element vector types. Now that's really cool if you want to make use of 512-bit vector pipelines in CPUs. CUDA at this stage only does 4-element vector types. And that's fine. That's what they need to do. But I really appreciated being able to leverage long SIMD pipelines within CPUs using these up to 16-element vector types. I really like the fact that OpenCL has consistent data types, such as CLint, and they mean the same precision on every platform. I found that really good because, as you know, some data types actually have different precisions, for example, on Windows or Linux. So consistent data types means consistent results across compute devices. So yeah, another of my opinions about SYCL, it's great that SYCL's following the same path as OpenCL. And there's heaps of different implementations that people are getting really excited about. But I did notice, I just couldn't help noticing that OpenCL underpins or is like the silent accomplice in a lot of these implementations. So that kind of gives me confidence that OpenCL is going to be around for quite some time, at least as a supporting framework for things like SYCL. So, a contentious topic. SYCL seems to be the way forward, but does it require the user to get really comfortable with C++ first? And is that going to get in the way of the science? And then the next question is, are scientists the end user for this? Okay, so there's a story behind that. In my postdoc days, I got really, really interested in C++. I got interested in polymorphism. I got interested in destructors. I got interested in classes and inheritance. And the lure of that power was very, very seductive. So I made things more and more complicated. But when it came time to debug this, and this is for my boundary research, when it came time to debug this, the complexity that I invested in started working against me. And so that's the reason why I have this opinion. Is C++ going to get in the way when it comes to SYCL? And the other point I'm making is perhaps Fortran is still popular for HPC projects because it is fast and well-written code is straightforward to read and write. So I'll just leave that thought with you. I'm sure we can discuss it another time. There are some challenges working with OpenCL. There are, large amounts of boilerplate code, but this can be mitigated through the use of reusable headers. And pretty much the folks that I've talked to that have been using OpenCL, they ended up coming up with their own headers that mitigated this complexity. So this, for example, is just some code to get or to query the available devices on your computer. And this code can be all wrapped up in libraries that kind of simplify this process. So you can mitigate that complexity through the use of reusable headers. You need to check all your function calls. So here I am checking some returns. Tools for profiling and debugging OpenCL. Well, I guess you can use the profiling tool. Yes, you can use the profiling tool for your chosen language, so C or C++. But then debugging kernels themselves, that has been traditionally quite difficult. There is a package called OCL Grind, which simulates a device and it checks. Oh, hello? Yes, sorry, it simulates, simulates a device and checks all your OpenCL calls. So that is possible ways forward with regards to debugging. Within events themselves, so remember those things that were attached to those balloons right back when I was talking about OpenCL. So you can actually use events themselves to profile your kernel calls. So that's another way to get information out about how well your kernels are doing. There is another challenge to working with OpenCL, and I think that's actually a really important one. Memory allocations are limited in OpenCL to 1/4, a minimum, of your available device memory. And so I just did a brief survey of the OpenCL devices on my computer. And, with the NVIDIA implementation, the limit was about 1/4 of the device's memory. Same with portable OpenCL, that's the CPU implementation I'm using. But the ROCm implementation, so that's using ROCm 4.5, that allowed me to allocate 14.6 of the 16 to 17 gigabytes of available memory. So yeah, that is something to be aware of, is that your device allocations are limited, obviously by the size of the memory on your compute device, but they're also limited by the implementation. Okay, so you do have to be aware of that. If you're making lots of little memory allocations, that's fine, but if you're making these huge memory allocations, then this will be a problem. Okay, so there are other ways to use OpenCL. You can use it as part of your favorite machine learning library, such as PyTorch or TensorFlow. You can use it through Python. So this is what I do with my industrial clients right now, is I actually use Rekner. And I actually have a training course that can help you do the same. You can also use OpenCL through a third-party library. Now we've talked about Pelagos, and ArrayFire is one particular library I'd like to put forward. It can use both OpenCL and CUDA as a backend, but it has a really cool, really easy to use interface for working with arrays. So yeah, that's another one. OpenCL as a research investment. So you can use C++ if you want to, otherwise C if you want to keep things simple. Okay, so OpenCL has been around for a long time, and I believe it will continue to do so. It's stable, great industry support. If you adopted this as part of your research group, we're thinking about minimizing the pain of porting to the next architecture. So you see these talks about how to port from, CUDA to HIP and vice versa. The pain would be minimized if you adopt a framework that works across all the different architectures. The latest version allows the standard room to grow. And the standard's not tied to the well-being of any one company. And just as I've said before, it's portable and math is consistent. So these are some good reasons why you might consider using OpenCL as a research investment. Okay, so now I'm going to go to the demo. And what I will do now is switch across to, so I'm just going to stop sharing and I'm going to share a particular window. Okay, can everyone see my?
Yeah, that looks good.
Excellent. Okay, so I'm just going to do a brief thing that I've knocked up for this talk. And that is doing image correlation with OpenCL. So convolutions or correlations are an integral part of things like convolutional neural networks. And yeah, what they are is essentially a math operation where you apply a filter to an image and you get some result, which is which is of interest to your neural networks further down the pipeline. Okay, so this is the maths of convolution, and this is the maths of correlation. But I think it's simpler just to have a look at a picture. So we've got an image here, and I'm just going to assume that at every pixel there's a certain value associated with it. Then I've got a filter. Okay, this is a 3x3 filter, and this is what we want to correlate. Okay, so if I was doing a convolution, this filter would actually be flipped upside down and then left to right. But convolutional neural networks don't care whether you're using a convolution or a correlation. So I'm just going to do a correlation because it's a little bit simpler. Wow. And so what we do with a correlation is that we have our starting point. So that's our origin, which is right here. And what we do is we walk in the 2 dimensions. And for every element, we grab an element from here. We grab an element from here, right? We multiply the 2 together. And then we sum that result to a sum. And then when we're finished going over the entire extent of the filter, we've got our sum, which we then put into our filtered image at the same location as the origin. So we've got our origin here, and then we do that. And then what we do is we then move this square across, maybe across this way by 1. Okay, now then this becomes our origin. And then we do this operation again, and then we put a value into here. So that's what a 2D cross correlation algorithm is. So we'll just do a brief flops count. So we need to do 18 fetches for this. So we need to do 9 fetches for our filter, 9 fetches from our image, and then 1 store here. Okay, so with each bit of our sum, we're doing 2 math operations. So we've got 18 flops that we're doing here. For a lot of scientific computing, we use 32-bit, which is 4 bytes per element. So our flops to byte ratio is quite low. And that means that we're going to be memory bandwidth limited. Okay. So if our flops to byte ratio was a lot higher than 1, then we would be thinking that it's more limited by our compute instead of our memory bandwidth. So what I've got here is I'm going to apply this filter to a whole stack of real-world images. So I'm just going to read in an image. So this is an image of the P'Con21 that I took quite a few years ago. And what we're going to do is we're going to apply this filter to this image here. And this filter actually happens to be an edge detection filter. So I've already gone ahead and done a bit of research as to what this filter actually does. So this is an edge detection filter. And so what we do is I'm just going to take this image and I'm going to make a big pancake of those images. And I'm going to make a pancake of size 1024. And so we just go ahead and make that pancake. And then I'm going to write out that. Okay, so our pancake is written. It's now about our stack of pancakes is 5 gigabytes in size. And what I would have done is I would have done, just to test or just to provide an example, I would have tried to do these correlations in Python. Okay, but it's going to take 2 long for me to do this. But what I got is 61 images a second. So that's the best solution that I could come up with. Python gave me about 61 images a second. So, and if I had checked my, correlation solution, you can see that this is actually what we are looking for here. Actually, I might have already run this before, so yes, that's okay. So this is what we're looking for. So we did our correlation stack with Python, and we're comparing it to a correlation operation with SciPy, and this is our result. So this is one of these images in the stack, and we can see that it's doing edge detections quite nicely. Okay, so now comes the OpenCL bit. So when processing multiple images with OpenCL, this correlation process can be farmed out to multiple compute devices. So each of these correlations here, we can just say that's one part of our pancake. And then what we do is we farm out bits, we farm out slices of our pancake stack to each compute device. And so we've got our code. I'll just start with our kernel. So this is our kernel here, and it's just doing the image correlation here. And then I've got my main application. So I'll just walk through the application. We've got some setup. So we just acquire our devices. We create some command queues. We create a memory for images out. And then we just read in our pancake of images to apply these correlations to. We allocate some memory. Then what we do is we create buffers on the compute device. Okay, so every compute device, I've got 3 compute devices in my system. So we create buffers on every compute device, and those are going to be used as inputs and outputs for our correlation. So we read memory in, we apply a kernel, and then we read memory out, and then we send that memory back out to our host stack of pancakes. Now, I'm using OpenMP to do just a dynamic allocation of threads. So I've got 1 thread for every compute device, and I'm using an OpenMP dynamic construct to send the work out to every compute device. So to send those pancakes out to every compute device for processing. So yeah, we write memory to the device, we enqueue a kernel, and then we read back out and then back out to main memory. Okay, so that's how we're making use of all the devices on our computer. Okay, so just to show you that I've got 3 devices here. And compiling an application with OpenCL is just a matter of including the OpenCL headers during the compilation, and during the linking, just including the OpenCL libraries. So it's really simple to get OpenCL working on, with your application. So now we saw that using this correlations with Python took about 60 images a second. If we try using just the CPU, I'm just going to run through a set of 1024 images. So each iteration is 1024 images processed. So if we just use the CPU as a compute device, we get an image processing rate of about 138 images a second, which is pretty good. It's a lot better than the best performing Python solution. The worst performing was actually the SciPy library, which did about 5 images a second. It's really terrible. So now we can use our GPUs. So I've got a Radeon 7 here in my system. So that's a Vega 20 architecture. And I've also got an NVIDIA RTX 3060. So I'm actually using the RTX 3060 and the Radeon 7 at the same time. And so we're getting an overall processing rate quite a bit higher now, using, a factor of 7 faster using the two GPUs. So okay, let's try again with all the devices on our system. Now, when I ran this before, I got about the same results, or sometimes worse results, than using just the 2 GPUs. And I think this is because of contention for memory bandwidth of the host. So yeah, we got a slightly worse result that time. So I would suggest just from this particular example that if you're going to use GPUs, just use GPUs, but you can use a CPU as an acceptable computing device. So I'm just going to read my images back out from file and plot the results, and we can see that we got the same thing as before. So this is our proof check that we did the right thing. Okay, I'm just about out of time, so I'm just going to quickly sprint towards the finish. All right, slideshow from current slide. And yeah, these are the results I've got for later. So you can actually download this correlation demo. It's open source. You can use it as a benchmark if you like. I'd be interested to see how this correlations go on Pawsey's new GPUs. So yeah, you can grab that link, and I can send it in the chat afterwards. Compute devices at Pawsey. So now that we've got a framework that works over every kind of device, then we can have a look at which devices are interesting. And obviously, those from a compute perspective, obviously the MI250 GPUs will be very interesting. They've got 208 compute units and 13,000 processing elements. And yeah, and a huge memory bandwidth. But have a look at the CPU. The pink teraflops of the CPU is now approaching a consumer grade graphics card. So I'm thinking that you might be able to use the new CPUs on Setonix as sort of like a poor man's graphics card, hopefully with an OpenCL implementation. So we've already seen before that Setonix is going to have 4 GPUs per per compute node, and all I'm saying here is that will OpenCL on CPUs be supported as well. My last slide, Pawsey training for OpenCL. So I'm working with the team at Pawsey, and we're keen on putting together some training on OpenCL, but also training on how to make good use of compute devices. So we're going to cover things like introduction to OpenCL. We're going to teach some survival C++ for scientists. As I've done here in the demo, we're going to go through an example application in a bit more depth. We're going to dig it out and have a look at it line by line. We're going to talk about how to make the best use of memory and cache hierarchies, tips for getting the most out of your OpenCL application. Hopefully then we'll have some good suggestions on debugging and profiling tools. And then I'll get you to do some relevant exercises and coding challenges just to get you or your students engaging with the material. So thank you so much for attending this talk. Thank you so much for Pawsey for sponsoring this talk. And thanks to the audience for attending.